Okay, we started maybe, or I admitted everybody a bit late, so we'll have another couple of minutes to give people an opportunity to join before I start with the intro.
Yeah.
Sinan, you might want to mute yourself.
Okay.
While we're idle. Okay, I think we can get started with the intro, and then people can join a bit later. So hello everyone and welcome to the EMinar. Today we have Kate Selway and Sinan Ozaydin. I'm not sure. I think Sinan, your last name gets butchered.
Ozaydin.
Sorry, say again.
Ozaydin.
Ozaydin.
Yeah, it's like Poseidon. Oh,
okay. Talking about well, mantle conductivity and their new tool MATE. But before I introduce well, both of them, I want to alert you to the next couple of EMinars. Now I always have this issue with slides not changing properly under Linux. So let's see if I can get this to work. Can you see can you see Yasu and Lucy? Okay, so we'll just do it like this. It's not the best way, but at least you can see what's going on. So next week we have Yasu Ogawa on imaging fluids in the crust and seismological and volcanological applications. And then the last EMinar of the season will be in 2 weeks. And we have Lucy McGregor, who is the SEG Distinguished Lecturer for this year, and she talks about multiphysics analysis and extracting the most from diverse data sets. So I think those will be both very interesting, and then we go into our well-deserved summer break, or winter break for those of you in the Southern Hemisphere. So let's see, of course now this doesn't want to change. I apologize for those slight technical issues. So yeah, Kate and Sinan have been working on sort of mantle conductivity, and Kate is currently a senior research scientist at the Future Industries Institute at the University of South Australia. And well, she did her PhD in Adelaide in 2007, and then has been working well at different places around the world: Adelaide, Yale, Columbia, Oslo, and Macquarie. And well, as probably many of you know, she's been working on this integrating laboratory and other results with MT for a long time. And Sinan just handed in his PhD 3 weeks ago, 4 weeks ago now, and was a PhD student at Macquarie Institute in the university, and did his master's at, okay, I can't pronounce that, at a university in Turkey. Boğaziçi? Okay.
Boğaziçi.
Okay. And he's been working on the structure of Southern Africa, and actually we've been sort of collaborating on this topic for a while now. So yeah, I'm also very interested to hear what you have to say. And with that, I will stop sharing and hand over the stage to you.
Unmute myself. There we go. Can you see my screen?
Yes.
Yes, fantastic. Thank you. Thanks very much for that introduction, Max, and thanks also to the rest of the EMinar team, Alan Jones and Stefan Thiel and Kate Robertson for doing all the organising. And thanks to all of you for tuning in, whether you're here live or watching this from the future, watching the recording. As Max said, we're going to be talking about interpreting, sort of, I guess, continuing this theme that's been in the recent EMinars about interpreting MT models. And specifically, we're going to be talking about interpreting MT in the Mantle and this tool that we've developed called Mate to do that. And this is going to be a slightly sort of tag team presentation. So the way that it's going to be structured is I'll give a short introduction now. And mostly what we hope for today is to really sort of use this as a video tutorial for the Mate software. So Sinan's going to lead that, but we're going to try to do that in a slightly conversational style. I'll be asking questions as if I were a new user, in the hope again that makes that a useful way for the rest of you, that'll be a way that you can clearly see how to use that software, and we can make it most accessible to people. And Sinan will then talk about how Mate, just one example of how he's applied Mate to some data in Southern Africa. And a few places throughout the presentation, you'll see this link to the GitHub, the GitHub location of the Mate files. So a bit about the motivation of why we would want to do this first. So MT provides really unique views on the upper mantle. Really, we have very few techniques that can see into the upper mantle. And by telling us about the conductivity of the upper mantle, MT is providing us really unique and important information. And that's kind of highlighted by some of these really enormous projects that are going on around the world at the moment, things like OSLAMP and US Array, also Sinoprobe, and also smaller scale surveys where it really feels like the earth science community is recognizing the value that MT can provide. But if all that we end up with is models with red and blue blobs, then I think that utility of the MT is going to be provided. It's going to be limited, sorry. So a couple of examples of projects that I've been involved in. Firstly, the top image from the Transantarctic Mountains, going from West Antarctica in the left, which is more conductive, to East Antarctica, which is more resistive, which maybe, you know, we'd expect. East Antarctica is older and more cratonic and probably colder. But of real interest here was the transantarctic mountains here, shown by this big jump in topography. And most models for the transantarctic mountains would suggest that that topography has a thermal basis. But as you can see, the lithosphere beneath the transantarctics is sort of the bluest part of the whole model. It's the most resistive part of the whole model. It's a really surprising result that tells us that there's something that we don't understand about how the tectonics are working in this region. At the bottom, a similar story. This was work that I did a few years ago in the East Africa Rift in Northeastern Tanzania. So here we have the Tanzania craton on the left, much more conductive than the actively rifting East Africa Rift and Mozambique belt on the right, which are much more resistive. Again, you know, the East Africa Rift is a rift that's much hotter. It's tectonically active. A lot of those models would have expected that to be the more conductive region. And certainly the seismic models show that to be seismically slower and interpreted as hotter. So actually in both of these regions, the MT results don't necessarily contradict the seismics, but show a different picture than what we would expect if we only had seismics. So these are examples where MT's telling, it's, you know, they're really exciting results because they're telling, MT's telling us things that are new about the Earth. But if, for us as MT practitioners, but also for the broader earth science community, if we're going to really use that to have a better understanding of how the Earth works, and if the rest of the earth science community is really going to take MT on board and embrace it for all the things that it can show us, then we need to go from those red and blue blobs to understand what that's telling us in terms of the temperature and composition of those regions, and what that's telling us for why the transantarctic mountains are uplifted or why the Mozambique belt is rifting. So within that, if we're trying to make those quantitative interpretations in terms of composition and temperature, there are some kind of general steps that occur in that. Generally, we start with a theoretical idea of what might control that physical property. That idea is then tested experimentally. Those experiments then generally have to be extrapolated out to Earth conditions. And then we calibrate them against the real Earth. We test them against the place where we know what the composition and temperature of the Earth is. So if we were, for instance, working with potential field data in the upper crust, then this process is really, really easy. We have no shortage of rocks that we can get our hands on, really easy to measure the density and magnetic susceptibility of those rocks, and to test our interpretations. Once we move into the mantle, all of these steps are much more challenging, but we can certainly still achieve them. So an example of this is the role of hydrogen in olivine conductivity, or just looking at olivine conductivity in general. So the idea that hydrogen might be important in olivine conductivity came about really from a theoretical basis. This was a paper that Shun Karato wrote in 1990, going from the idea that, well, hydrogen diffuses quickly in olivines, so therefore we might expect it to also enhance olivine conductivity. And I'll go into a bit of terminology here because Sinan will go into this later. This idea was really that the bulk of olivine conductivity can be considered the sum of proton conductivity, which comes from hydrogen, from polaron conductivity, which is really electrons moving, and then at higher temperatures, ionic conductivity, where the iron and magnesium atoms themselves will move. So that paper came out in 1990. It wasn't actually until 2006 that experiments were run to test that idea. And since then, a lot of different experiments have been run on olivine conductivity and hydrogen specifically. And those experiments have all shown that, yep, that idea was correct. Hydrogen does really impact olivine conductivity, although the magnitude of that effect has differed in some of those experiments. But also all of those experiments have been extrapolated out. So they've been run at different temperature conditions, different pressure conditions, and they've all been extrapolated to consider the full range of conditions we might see in the upper mantle. So then, for instance, this more recent paper from 2014 looked at those extrapolations and suggested that actually maybe those experiments don't disagree quite as much as they seem like they do. And it's some of that disagreement is a function of the different extrapolations made and different considerations of errors. We're also at a stage where we can calibrate some of those interpretations against the real Earth. So again, this is something that Sinan will come back to later. But although it's much harder to calibrate against the mantle than the upper crust, we do have places where we have a lot of xenoliths that come from the mantle, and we do have a really good idea of what the composition of the mantle is, and also where water content measurements have been made on those xenoliths. So we again have a good idea of what the water content of the mantle is. So we can compare that, that knowledge of what the composition and temperature of the real Earth is with what our MT interpretations say, and check whether we're sort of in the right ballpark with our MT interpretations, or if we're totally missing the mark and there's got to be some other really substantial factor going on controlling conductivity in the mantle. And then there's always new ideas as well, and this is just one example of a recent paper looking at, for instance, how titanium content in olivine might also affect its conductivity as well. And there are really lots and lots of these kinds of experiments. And as you can imagine, also then you could, there's certainly no shortage of compositions that you could be testing the impact on conductivity. So through all of these experimental data that we have, we can say that there are some key factors in making quantitative interpretations of MT in the mantle. And the first of those, probably pretty obviously, is the conductivities of the individual mantle minerals. So, we need those measurements of how the conductivity of olivine, garnet, pyroxenes, and other minerals like amphibole and phlogopite. What are those conductivities? How they differ with temperature, iron content, water content, and things like that. Because hydrogen is such an important control on the conductivities of many of those minerals, the way that hydrogen partitions between those minerals is really important too. And again, there are a lot of experiments constraining this. So for instance, in this sort of cartoon example here, we might have a rock with a small amount of clinopyroxene, not enough clinopyroxene that it forms an interconnected network. But if that clinopyroxene is really, let's call it really thirsty, and it sucks up a lot of the water from the rock, then it can actually lower the overall conductivity of the rock because it sucks water out of the phases like olivine that are the more bulk phases that are interconnected. So considering that, hydrogen partitioning can be really important in understanding the overall conductivity. And again, sticking with hydrogen, it makes the minerals more conductive, but we can't just keep shoving more and more hydrogen in the minerals. There's a solubility limit that those minerals have. And again, those have been tested experimentally. But again, a lot of those experiments have differing results as well. And finally, a really important key is the geometries of the mantle rocks. We can perfectly know what the composition of the rock is, we can perfectly know what the conductivities of those minerals are, but we need to know the geometry to know the bulk conductivity. We could have a really highly conductive phase, but if it's not interconnected, then it won't affect the bulk conductivity in the same way as it would if it were interconnected. And there are lots of different models like an Archie's law or Hessian-Strickman bounds that we can use to define that geometry. And of course, as we do all of this, then there's always more experiments, and there's always the possibility that there are other phases that might cause conductive anomalies in the mantle that we haven't previously considered. So as we were looking through all of this, and I guess with this goal, as I say, of trying to move from red and blue blobs in our models to knowing what that means in terms of temperature and composition, it sort of struck us that the real roadblock for us right now as an MT community is not so much a lack of experiments. It was a lack of, it was a difficulty in being able to implement those experiments. There's, a lot of these mineral physics papers, it's like they speak a slightly different language, and they can be quite dense to get into and to understand the experimental constraints on them. Which experiment should I choose over another experiment? And just the practicality of getting those equations out of those papers and using them to be able to interpret our models. And in practice, it's not something, if you're a standard MT practitioner, you've gone out, you've collected your data, you've made your model, you need a couple of paragraphs in your interpretation in your paper. You know, maybe it's a year's worth of work to really delve into all of those experimental papers and figure out what that interpretation is going to be. In practice, people just aren't going to do that. And that was our motivation for building MATE. Essentially, that Sinan came along, was doing a PhD and was doing really great work in this space. That he could spend all of that time delving into all of those papers, and then build this tool together so that that data is already there for everybody. And instead of being hopefully a year-long process to get that interpretation together, maybe it will take a day or two to get that interpretation for your model. One thing, so I'll hand over to Sinan. Now, one thing I will say about the way we put MATE together is that we were quite careful to do it in a way that was not very biased. So as I say, there's lots of different experiments, and we didn't build MATE in a way that said, okay, well, this is the experiment that we prefer. We built MATE in a way that allows the user to choose which experiments they want to use. And so that does mean it's not something that somebody can go into and spend maybe just 10 minutes looking at it and build an interpretation. There does need to be some interactivity to understand which models to choose. But Sinan's also, I guess, summarized all of that information about the experimental parameters, things like, you know, what were the PT conditions the experiment was done at, was melt present, all of the different things that might tell you whether it is relevant to your setting that you're trying to interpret, or whether you should choose a different model. So yeah, with that, and yeah, we hope that all of that information is really clear, both in the documentation that's with MATE, but also hopefully in what we go through today. So I will hand over to Sinan to start going through the tutorial.
I unmute, yeah. Well, it takes a lot for the introduction, and again, I also want to thank everyone giving to the opportunity to present our stuff here. And I'm just gonna show really like how the MATE really functions, and then as Kate told, I'm gonna go into a little bit of like a case study, as like how we use this tool, and that so that it might inspire you to maybe use it as well. So first of all, you can access this code from this GitHub repository. I guess like we can access it through some link we'll provide later on the chat, and maybe in the YouTube about section as well. And it's basically, this repository has this basic information, and there's a link to the paper as well. And there is extra information in the paper about the interpretation of a generalized cratonic mantle and what could those be, and more intricacies I'm not going to go into super into detail during this talk. And so you can check out this paper as well, and there's supplementary material also has good information on them. So if you are stuck on a paywall, just send me an email, I can send you the paper as well. So installation, I mean, it doesn't really require any installation, but in whatever operating system you use, basically you just like download from the downloaded repository, you can just go Python MATE, and it doesn't require many libraries, like just general use libraries in the Python. And then you can, of course, have it in the Conda package management system. And for some reason, the Matplot 3.3 is slower, so that's a heads up a little bit. And you can, if you can lower that version to the previous one, for some reason it works much slower in general. So it'll be much better if you do that. And if you are operating in a Windows environment, you can also create an exe file with basically going through in the environment and typing Python 3 setup exepy. So I'm going to here basically download it to this area, and I'm just going to open a terminal from this repository I entered and just going to run Python 8. And this opens up the general window we see. So here's the canvas that the things are going to be plotted. And mainly there are 3 sections to this. One is the setup buttons, which basically where you like give detail to your parameters and your entry and input of the geotherm, the composition and everything. And then there is this action buttons here where you have basically like calculating and executing whatever you entered and then reset it and solve for input data as well. And these menu bar options have more intricate details like oxygen fugazi selection or data input, like if you want to input the thermobarometer data, and then you can just select an input. And probably most important one is here is the water calibration correction, which people should probably look over, like is because it's like how hydrogen partitions into things is kind of an important issue. So I recommend looking into what are those details are, and saving figures and writing data, basically pretty straightforward interface. So in the first part, what we want to do is for the start is to basically enter a composition. So entering a composition happens with these 3 buttons really. The first button opens up the text editor where you can enter the file. So the file has to be a CSV file and like a CSV with a comma separated value. And for this reason, it's probably best edited by an external thing like LibreOffice Calc or like an Excel kind of spreadsheet program. And here you
so
can
Sinan,
see,
if I can jump in there. So it looks,
yeah,
to me as a brand new user, that looks like a complicated file with lots of different parameters. Are they all necessary? Do I have to change all of those parameters?
not all of those parameters are necessary, but most of them are going to be activated if the options are going to be used. The most necessary ones are the bulk water content, depth, and the composition. And the other ones are only activated, they're optional. But the important part is that they have to be just some value entered there. So you cannot just like leave it blank. Otherwise, it will give you a message box that says, okay, enter something. This file doesn't look right. So you can have a reference for that, those example composition files in the repository. So you can build your...
Those are example files that you've provided with the repository?
Yeah, they can be found in the repository section in the example composition. Some simple ones, and then you can start editing from there, which would be the best if you are kind of feeling lost with all the different things. So I'll try to run all of it, like what are all these parameters. It's basically depth has to be the top of the layer. And we'll have the bulk water composition, and this will be distributed to all the minerals with the given input. And will be the mineral fractions: olivine, orthopaxine, clinopaxine, garnet, spinel or chromite, phlogopite, amphiboles, and a conductive optional thing you can enter, and enter your resistivity as well, or conductivity.
So that might be, if I thought I had graphite or something in the rock, then that would just be another conductive phase.
Yeah, like it will be probably best like something that doesn't involve in the water distribution, and then like a graphite will be a good example, like, and not temperature dependent, so that it will be a stable value everywhere, or at that layer, you know, that conductivity and doesn't involve in the water distribution too much. And the next ones are the iron contents of the nominal anhydrous minerals, and aluminium and titanium in olivine, and orthopaxine, which comes in for some calculations in conductive measurements and solubility measurements. And then what we have after is the M parameters, which are the interconnectivity parameter for the modified Archies model, which is the lower your value is, like the more interconnected you are. But you probably have to look after like whether you are entering actually a sensible thing. So for instance, in a model, you want to enter phlogopite super interconnected, you can, and test that. You can enter, just change this to 1. And that will be the limit for interconnection actually. And later on, we'll have that conductive minerals thermal conductivity. And this is probably sounds random, fluorine content of the phlogopite. So that comes in the phlogopite conductivity. So you can enter these values as well. The value entered here is the median value from all the rocks from the georock I calculated. So that will be a good place to start as a default value. And this is the olivine, OGS is the olivine grain size, which comes into the calculation for the diffusion. When you connect the diffusion to the diffusion of hydrogen species into the electrical conductivity in the region. And if that's the case with the grain boundary, diffusion is active. So if you change this value, your grain boundary diffusion value will change. And this is a default value for heat production in the mantle, which is like a best fitted for the Hasterick and Chapman that we mostly implement.
So before you go from that, so if I was, are you able to bring up the CSV again?
Yeah.
So if I was a new user, and a lot of those parameters, you know, I have no idea what the fluorine content in my phlogopite would be, or what the titanium content in my olivine would be. Am I pretty safe to just, if I'm starting from your CSV file, am I pretty safe to just stick with those values for those things that are a bit more in depth? And I would just make sure I change the layer depths, the bulk water content, the proportion, the olivine, the proportions of the minerals that I think are in my rock. And then if I want to use an Archies law, then I would change those Archies law values. Would that be, if I just did that, would that be pretty safe?
Yeah, I think the values I entered as default are pretty conservative choices. Yeah. So it'll be fine for if you want to input those.
Yeah, great.
So the thing to do here is that you basically either can enter here, of course, but the best way to, of course, to just upload the file here, and then you can save this file as well from this text editor and submit. Click submit data. Without clicking submit data, it doesn't work.
Mhm.
And in many of the program, there is info sections I wrote where like goes into detail of what are those parameters are like, or what is happening here. So you can also click these buttons to have more information. So in connection to the composition entry, we'll have the depth range section, which basically the most important thing is that you have to be sure that this moho depth has to be the same as the first layer's top layer. If not, the program will warn you that, okay, this is not matching, please change it to moho depth.
Mm-hmm.
And in the composition setup section,
can I just ask a question, because I know what the answer is? If I was in that depth range box and I wanted to change the depth, those layer depths, how would I go about doing that?
Oh yeah, you have to click this and enter and not change from the box, because it doesn't do anything actually.
Mm-hmm.
Yeah, sorry. And yeah, that's how it goes. And in composition setup, we'll have some options for composition. So if you entered Flogopite, you have to open this box, and if you enter Amphibole, you have to click on this as well. And in aluminium dependency is most related to water partition coefficients. I'll go into detail later on when we are at that stage. And
so do you think, again, if I was just a new user, would I be better off clicking aluminium dependent or aluminium free in that option?
I think aluminium dependent will be fine. Like,
yeah.
Since I'll provide the conservative values for the aluminium, so even if it is going to be the free or dependent, it will be fine. Yeah. And yeah, the next thing to do after you submit the plot composition, and you'll have the 3 boxes with the changes. If you change some other stuff, basically, let's change the iron content of the oil part of the pyroxene, for instance. I'll have a different plot here. And the next thing you want to do is construct a geotherm for your build your dependency. So if you click the geotherm, a pop-up box opens. So there are multiple ways to go to constructing geotherm here. Is that the default section is the one here is the cratonic generalized geotherm of Hastrick and Chapman 2011, which puts the 26% of upper crustal radiogenic heat production to a 16-kilometer layer at the upper crust and builds on the rest as it goes. And if you don't want to use that as a crustal heat generation, you can always select this one as generalized cratonic mantle composition and make changes by yourself in these parameters.
And if I were to make changes in those parameters, would it be the same as changing the depth range, where I click on the box to make a change?
Everywhere. That situation is global in the program in general. And if you click the composition dependent, it will use these functions that are basically thermal conductivity changes with pressure, temperature, and like things like iron content for some. So if you build those, there's an internal thermal conductivity library, so that it will connect to that, and whatever it will create dependent on that.
Mm-hmm.
So if you don't know much, you just best go if you're in a cratonic composition for the default section. And for the and you can also, for instance, you not very different type of geotherm here. you can always input a geotherm from a CSV file as well. Like, yeah, you want to calculate the ocean, for instance, which is a very different environment. You can build an ocean geotherm as well, but yeah, you already have it, so why you rebuilding it? Yeah, and then you can just enter from a CSV file to.
And so that would just be a CSV file with depth and temperature in Kelvin.
Yeah, and yeah, there's input geotherm properties. So if you enter that, like, you can select the input properties. So in the info, there is also like how to enter the CSV file as well if you click the info. So we go with the generalized cratonic composition for now, and then if you plot geotherm, we'll plot a geotherm. And one thing I also want to go through is you can, for instance, input thermobarometry, which I know, for instance, I know it's the Celsius format. So you can change this, and you can change the uncertainties in this. It will depend on your thermobarometric method. And I have this file here. For instance, if I plot again, it will be that. One thing we can do is also solve for this depending on whatever MOHO depth and crustal heat generation is we used. So if we select, it will solve us for a geotherm. So in general, for instance, the program works as like it lays, imagine an array at every level. There's an array appended whenever you click one of these plot buttons. So whatever you use in the next one, it will be the last appended value. So if you want to clear this array, you just go to geotherm reset and plot geotherm. So you end up with the only last result. So it will effective in the every stage. And the next will be the water parts, which are the water partitioning and water solubility sections. So in these sections, we'll have an area where we can handle the partitioning models. And this can be selected. The pyroxenes can be handled together as named orthoparoxenes and chloroparoxenes, but it will be best handled independently, probably. And
so by that you mean if they're independently, then the orthoparoxene water content is calculated independent from the clinopyroxene, and otherwise they're all just the same.
Yeah, otherwise they'll be, you can put them in an umbrella as pyroxenes. Yeah, but yeah, because they are differing, but like sometimes you can do that, of course.
Sorry if I interrupt you guys. I mean, usually in these EMinars, we have kept questions to the end, but I think because you're already doing this sort of semi-interactive thing and there's a lot to go through, I just wanted to interrupt you because there was a question in the chat. Now, can you also, or the new other, if you have other questions, please put them in the Q&A section. I think that's better as a record. But so the question was how to determine the depth of the LAB. I didn't seem to see the input. I mean, you show the LAB here at 200 kilometers, but where can you tell the program what the LAB actually is?
Yeah, so there is not really an input for LAB here, because we're not solving for like a mechanical boundary layer. It's just solving for a conductive geotherm. But what you can do is this, at this layer, you can put the depth range as this in the MOHO section, in the maximum depth. If you change this, it will be changed basically. Yeah. But yeah.
But okay, this is now a question coming from me, and somebody who knows very little about these things. So sort of maybe probably one of your potential users. Doesn't the geotherm depend on the LAB depth, because that's where you go from adiabatic to conductive heat transfer? So shouldn't your geotherm change a bit if you put the LAB a bit lower?
Yeah, I didn't put in for the adiabatic temperature, but it can be installed in the future because I mostly delve into the cratonic mantle as from now on. So the solving for adiabatic, where you basically lose all of your sensitivity in the MT. But for now, it is basically where you can meet with the adiabatic. But yeah.
So Sinan, so if you wanted the conductive geotherm to extend down to 220 kilometers depth, how would you make that happen?
Conductive geotherm to 220 kilometers depth. Yeah.
Yeah. So like, yeah.
Yeah. All I do is to change the depth range, basically. Yeah. But it won't solve for adiabatic geotherm for now. Yeah.
Yeah. Okay.
Yeah.
Yeah. So it's still just plotting the same because you didn't recalculate the geotherm. If you recalculate the geotherm with that maximum depth at 220, then it,
yeah.
Ah, okay. I didn't see that because I was a bit irritated that the depth changed to 220, but your black line stopped at 200. But now you clicked on plot geotherm and then it changed.
Yeah.
Okay.
Yeah. Where was I? So
water partitioning, yeah.
Water partitioning. So wanting to, so it can be handled independently, and then if you open the Parexine box, you'll see all these different partition coefficients from different experiments with different ranges and assemblages is indicated here. And also you see the type 1, type 2 type of things. And these are basically, if you put on the info box, you'll see that the aluminium dependent function, for instance, type 1 is all pressure range, which is basically some people fit to the aluminium content over the water and orthoparexine, hydrogen partition with orthoparexine and olivine, because it is kind of a relationship there, and you can use this relationship. For instance, the first one is this fit that I made, and then there are other fits to this pink line, for instance, so you can use between them. And the type 2 is the Alban-Vasselin, is that if you are only in the Garnet pressure range. And type 3 is the pressure dependent functions. Some studies provided those options. Type 4 are basically the single value, just one partitioning coefficient, basically. And these are like the, you can see here. And type 5 is the CPX, OPX dependent CPX all values, which is implemented because in general, CPX, the partition coefficient between CPX and OPX is usually much more stable value between two, whereas if you want to go through the experiments between CPX, sometimes it doesn't form quite well, so it is like a high value in the experiment. So it is better to calculate the things between like this type 5 value in general for the CPX. Okay.
So this is then where earlier on in, what's it, the composition setup, where that aluminium dependency, whether we choose whether it's aluminium dependent or not, then this is where that becomes important, right?
Yeah, exactly. So in that sense, composition setup can be used. If you want an aluminium model, for instance, you can enter from here, like the novellas, some other studies, you can check them out.
And this is defining how the aluminium content of orthoparexine changes with pressure.
Yeah.
Yeah.
So like an example could be found in this figure. And this the thing I fitted to the Archean xenoliths from South Africa. As you can see, there's the aluminium content of the Archean and Proterozoic regions is quite low in general, whereas the Phanerozoic sections are more follows the experimental melt existing curve, for instance. So you can think about this when you're interpreting your values as this could be a contributing factor from your age of your mantle as well.
So although, you know, as I said before, we haven't put in default choices for these things, but if I was looking at MT in a pretty stable tectonic region, would you have suggestions for which partition choices you would recommend?
For this stable region, I think I could recommend, if it's like an Archean region, I could recommend my orthopyroxene fitting model with the P, or maybe because of the nature of the Dimucci 2017 model made with the subsolidus experiments, which means like there is no melt existing in the environment. If you are dealing with a cratonic environment, for instance, you might want to choose that more. But like if you're in an oceanic mantle, then you'll have to be dealing with another processes, basically. So those other stuff could be more applicable to your study. And yeah, this is all the other stuff with the garnet similar. And from the water solubility, so we can choose to plot or not plot the solubilities, and you can select between the models here, and then you can also choose to use the water distribution calculated from these models to is the maximum limit, so that you know that, okay, this is my maximum amount of water that can be calculated. So you can choose that to be yes, and if you plot water now, for instance, in this section we entered, you'll see that saying these sections are over the line of the water solubility limit.
And so that's that line is what you inputted in the composition entry of what the water content of your composition was.
Yeah. So for instance, we can change this now to be like more reliable, like you can change the water content to 0 for the first layer. And then see no errors will be going to be produced.
Yeah. And then just to clarify, so you had a bulk water content in that lower layer, I think of 100 ppm. And so those so that black dashed line is that bulk water content. And then the different colored lines are the water contents partitioned into those individual minerals by the choices that you made in the water partitioning section.
Yeah.
And then maybe just to clarify as well, so then those shade regions behind are the plots of the maximum water solubility. So for instance, am I right in saying, so the reddish region is for garnet, is that right?
Yes, and then because water partitioning is very similar to olivine, we have seen the region is a little bit smaller. So like when it crosses the limit of these, like the end of the field, you're basically over the solubility limit. Yeah.
Sure. Yeah. So then, but yeah, so that red shaded region shows the whole field of possible water solubilities in garnet.
Yeah.
And then the green region sits behind the red region as well, right? So we're going from 0 up to that maximum of the green region, and that's for olivine.
Yeah. I tried with different colors, of course, but like it makes it like a mess, really. So
Yeah, no,
if you
it's just,
transparent or something. And then the next will be the selection of conductivity models, and we'll see similar appendages as well in this. And let's look at the olivine, for instance. If you click, we have different asterisks involved in these areas. For instance, the meaning of these can be found in the info, which like models including iron dependency, models with higher Fe content, and effects of oxygen fugacity, or derived from lattice hydrogen diffusion or grain boundary diffusion as well. So in that sense, one has to be like sure that, like for instance, DI 2014 is a whole model that includes all proton, polaron, and ionic conductivity. And then you have to go, like, if you want to just use the proton conductivity of this, you can just use the proton here. And then what you want to do later is to change the dry conductivity preferences from whatever is in here. For instance, you can use a chromite-rich dry environment for the rest of the thing, and then add the proton conduction of the dye, so mixing things up.
So to clarify, what you just did by making those changes then was saying, okay, I want to select the proton conductivity from the DI 2014 experiments, but I want to take the dry conductivity, the polaron conductivity from Constable 2006.
Yeah,
so you
exactly.
can mix and max the models like that. Yep.
Yeah. And yeah, this also applies to the diffusion models as well. Like, for instance, if you choose one of these, like grain boundary plus novella, which is a lattice diffusion plus the grain boundary diffusion model. So if you choose that, of course, it will go to the dry conductivity of this, will be handled by this, because there is no like informed in those experiments.
Yeah, because that experiment only tells us about hydrogen.
Yeah. So it doesn't matter even like if you enter proton, polaron, whatever here. So automatically goes to them. So similarly, you can, pyroxenes could be handled or like not handled together, or garnet, you can change the amphibole phlogopite, and yeah, that's basically it. And for the conductivity, another thing is the mixing models. You can choose anything between them, Jones, Archie's law, all of these, and Archie's law also reverts back to the selections you made on the interconnectivity of the models here.
Yeah.
So if you plot conductivity, you'll see a little effect on the hydrogen on the olivine, not olivine in general, peridotite. We didn't put in here. So one thing you can, so next thing you can do, for instance, if you have empty data, for now we only can either use a MODM input and select your data, or like input a CSV file as a profile with depth, and so the format is in the info as well. And
but that would be a CSV in depth and resistivity.
Yeah. And if you, let's go through the MODM file, for instance, one of them, and conclude that. So if you, for instance, you can go for the plotting section first, open up a window, and for instance, we want to go to plot to 128. We can go to select empty data 128 and submit selected data, and then for plot conductivity it will appear here.
So this is the resistivity profile at that point in the model of that station 128.
Yeah.
Yeah.
Yeah. Similarly, you can import a CSV file, which I have the same thing here, I think. Should be. Wait, sometimes it have errors like this, and then the best thing to do is to clear all. Yeah, do it again from the start.
Yeah.
The most of the things will be here. And we'll have the stuff here. So one thing also you can do is to solve the water content for every entered parameter in that thing. So basically click after you selected your parameters on water partitioning, whatever you decided. For instance, I want to also decide on to choose these preferably.
Yeah, okay, so can you talk through what you're doing here?
So I chose the water. So water calibration is kind of important in like selecting the model, because like it differs quite a bit if you are considering different calibrations for
And so this calibration would be what the experimentalists use to go from their kind of raw data to turn that into a water content, right?
Yeah, exactly. So yeah, they are mostly done with FTIR calibration, and to do calibrated, if there is a more reliable measurement mean, then they calibrate those to that as well. There are more informations in the paper if you want to go on about it. And what you do is just like solve water. This will take a time. So what it is doing is just like brute force searches with the 0 to the solubility limit you selected now. So it searches for all the layers, what will be the water content, and finds the solution for that.
And this is searching for the water content that will match the profile data that you've input.
Yeah, exactly.
Yeah. So maybe while we're waiting for that to run, if you could explain a little bit more about the calibrations. So do you have advice on what calibrations people should choose? Should they go with what was done in the original experiment, or what would you suggest?
For the calibration is as people more suggested, and for the Olivine, for instance, the Witter's calibration to be the most reliable one, calibrated with ERDA measurements, and but some intricacies come into, and for Pyroxene and Garnet, the most reliable one still is the Bell 95 calibration. So these will be the best options probably, and whatever water content if you want to change as well. So you want to compare to something, you have to correct those values as well if you want to.
Yeah.
So be wary of that probably. So the correction factors can be changed from the repository that it's in a file called params CSV. So in that file, you'll see the correction factors, and if you want to, you can change those factors, but I use it depending on the demo sheet in Wolfgang Casanova 2016.
But your default suggestion would be, if you're calculating the water contents, use Withers for Olivine and Bell for Pyroxene.
Yeah. And as you can see, we don't have much water in this cratonic area, and for the conductivity models we chosen. So what we can do after we start is that we can change the figure properties from here for different selections, upper with plot bounds, and we can save the figures like similarly, just like gonna be, yeah, basically very simple function. And then you can also write the data as well, whilst basically going into there. And that is basically it for the general tutorial for this.
Can I just step back just to
to
clarify for that water content calculation? So you made the calculation, and then it's showing the results in that water content plot, the second one from the right.
Yeah.
So the shaded regions are still the maximum solubilities, and then the other lines are the water contents it's calculated for the bulk water in the black dash line and individual minerals. So here we're seeing it's putting a bit of water, what's that, around 100 kilometers beneath 120 or so, there's no water. But shallower than whatever it is, 70, or I guess shallower than like 80 kilometers, it's not fitting that profile because it can't put enough water in it because of that limit from the solubility model.
Yes, exactly.
Yeah. So now you've changed the solubility model and it's putting more water in, is that right?
No, I just changed to the log scale,
okay.
which you can do it from the figure properties in general. And yeah, if there any questions for this, maybe we can take it about.
Yeah, I think maybe it's a good time to have some questions. So please, if you have questions on this tutorial, sort of start typing in the Q&A. And actually, I can bridge the time while people are typing because I have a question. Because I think I'm probably, a possible audience for your tool. Yes, I've read maybe a dozen or so of these mineralogical papers over the last 15 years. So I have, what my friends typically call dangerous half knowledge. Yes, I've heard these names. How much am I protected from sort of creating a complete mess by, for example, selecting? You have these sort of mix and match things, like matching things that are inherently incompatible. I don't know, water solubility model with a dry olivine model and something else that are based on sort of absolutely incompatible assumptions. I mean, can I do this, or will I get a warning, or how much protection is there?
And you mean incompatible assumptions for?
Well, see, I mean, this is sort of something I don't know. Yes, I know about like these olivine measurements, and I know, there are things like this oxygen fugacity is a term. Yes, I've heard it many times. I know it's really important, but I don't even know sort of exactly sort of what it means. But I know the mineralogists always go on about it, and that you have to make sure that it's sort of correct and so on. So can I make a sort of combination of things there where, I think, okay, I like the, Karato is famous. Okay, I'll take his stuff.
Yeah.
And then here, whatever, somebody told me the buy model for this is great. And I sort of mix and match them. But then if I sort of put this in the paper, the reviewers tell me, okay, this makes no sense whatsoever because something is exactly like doesn't work together at all. Is there a possibility to do that?
Yeah, I mean, I think one thing to there is definitely a possibility you can create a lot of things, definitely different incompatible things, but it's better than having like to have a go, okay, this is the best model, and then another thing to just like, okay, I calculated for different models and let's see how they operate. And one of the things I wanted to build this as well because I realized this and then said, okay, I have to calculate all these different things at all times so that I should have a better operating system to do all of these differences that could happen, so that at the end I'll have a better system that could easily change between, okay, what if I change what happens to the guard as I choose, and then what happens to a different thing I choose, and then I can have a better grasp on what's happening. And then if I have really messed up things happening, I could just like, okay, how can I justify that this is not probably a thing better, probably, if that answers it.
Yeah, no, and I mean, I completely understand that the alternative would be to have this really sort of restrictive thing where you decided, okay, whatever, Yoshino is the best and Dai is, you know, the best for that, and you know, there's one thing, and then I can only within what you ever decided is reasonable. Do things, and that also creates very big problems. So I guess the take-home message for somebody like me is, so in case of doubt, stick to the defaults and don't move away from them too much unless you know exactly what you're doing, or at least, you know, have read a couple of papers around this, and don't just, I mean, because like in some cases you just sort of, you know, click until something happens that you like, yes? But of course that can
except
be
I would say
dangerous.
there, Max, is that one thing that's really important to note is that in most of these options, what will, you know, if you click on conductivity models, the first conductivity model that comes up is not necessarily the default conductivity model. It just might be the first one in alphabetical order. So if you don't make a choice, then the choice that's in there is not, don't think that that's there because it's like a default safe option. That has not been done. So yeah, for instance, yeah, Dai 2014 is the first in that list, just because of an alphabetical order. So it is important to make a choice in all of those options. And I think really you probably do need to go to the step of clicking on the info button and having some idea from that of you know, what are the broad parameters that these people have chosen. So for instance, in those conductivity models, the models that Sinan was talking about that are the diffusion only models that are a bit more, you know, they're not necessarily incorrect, but they're a bit more specific and a bit more maybe experimentally out there than just taking an olivine crystal and measuring its conductivity. So maybe you would avoid those things if you just wanted to do things very simply. But that level of information should be there in the info button.
Okay, yeah, but I mean, maybe as a suggestion to you guys, and I don't think anybody would fault you for that, or in the sense of you make a table of, okay, this is maybe a reasonable starting point for, you know, these 3 or 4 scenarios. If that's part of the documentation or so, I think that can help somebody like me at least to know, okay, this is where what I base things on, and then I go into things specifically when I see the need. Yes.
Yeah, I would agree. I think that's a good suggestion. Yeah, and now that I think part of it was also to make sure it was able to get through review. Had we chosen, you know, anybody's experiment over anybody else's experiment, that would have inevitably led to difficulties in the review process. But yeah, I totally agree that in practice for people that that kind of advice would be good. So yeah, thanks. Yeah, we'll take that on board.
Yeah, and there was one question in the Q&A which somehow sort of disappeared. I'm going to read it.
Yeah, sorry, I typed a text answer to that. Sorry, which is
okay. I'm just going to read it because we're doing this YouTube. We're putting it on YouTube, so the text answers obviously don't appear on YouTube. So Matthew Como says, you show examples here only in the lithospheric mantle, not in the astenospheric mantle. Correct. So is it only?
Yeah, and so my answer was that technically, yes, this is designed for the lithospheric mantle, but theoretically, if you put in compositions that were relevant to the asthenosphere and a geotherm that was relevant to the asthenosphere, And then especially, you know, when you're making the choices of those, you know, which experiments you choose, you might want to choose the ones that were done at higher pressures and higher temperatures. But theoretically, those results should be relevant for the asthenosphere if you did that. Would you agree?
Okay, but then what happens with melt?
There's no
Yeah,
melt.
there is no
Okay.
melt, but I am planning to add in melt in the near future, so there'll be a upcoming thing. So, but
Okay.
anyone also wants to help in build this, for instance, wants to do it right now exactly, I'll be also good to have a helping hand to putting this melt as well.
I suppose initially, for a simplistic option for melt, you could use that additional conductive composition parameter in the composition entry, and there would just be no kind of petrology involved of how the melt interacted with the solid. But I guess you could just consider it an additional conductive phase potentially.
Yeah.
Yeah, I think that's it, at least for the moment with questions. So I think, yeah, it would be good to see some example of this in action.
Oh, yeah. So I could, I was planning to show the recent paper we published on the geophysical research letters, and we basically made a case study in southwestern Kapwal Craton, and we basically wanted to answer like, okay, these xenoliths and xenocrysts we have, and they have water contents and certain metasomatic imprints, and to what ends are they representative, and how they are compare if we want to make quantified interpretation with them. So we choose this Kimberley area because it is like super rich in kimberlites and databases we get from Bill Griffin. And what we have here is first of all, talk about the xenolith and xenocryst information. The first figure is basically a histogram where the garnets, the 34,500 garnets originated from, and which type of rock they are coming from, and more specifically, which type of metasomatic imprint they have. For instance, the fertile, the green parts are where you have the fertile signature. This can be either subject to metasomatic imprint or never really depleted mantle. On the yellow parts with depleted larsolites and Harzburgites are where there is not much major elements and trace elements like depleted, and this includes possibly the volatiles such as water and carbon and stuff like that. And then so to compare, we basically have these two geotherms constructed. One is from the Garnet geotherm and the other one is from the two pyroxene geothermal barometers. We also mainly more inclined to favor the pyroxene thermobarometer because the literature, it is, say, more reliable, and our xenolith water measurements also mostly lined up with this as well. So what we did is did the 3D empty immersion, and we make the sensitivity tests, and we see that below 160 nanometer we don't have much sensitivity, and the block between those layers we have a sensitivity range which can be defined by this inclination trend. And then we also have this Kim 15 station, which is a more 1D characteristics. So we made a probabilistic inversion on this, and we see that in this layer, it's mostly matching with this 3D inversion as well. So we use these models to calculate the water contents for both geotherms cases. and basically compared with different Olivine conductivity models. We entered as in peridotite, and mostly what we see in the calculated amount of water contents decreases with depth, and this matches with fertility depletion trend of xenocrysts. And from the both geotherms, water contents for the Gardes and dye broadly falls into uncertainties derived from MT, which suggests there is no like super drastic uh, fall apart from the what is expected, but there are some different fittings to this thing which gather from different kimberlites, and this suggests a local metasomatic control is still apparent. And in this case of the depleted section, this could be a different story. We'll come to that later. And what we have is that also another thing that we have to look for is the phlogopite, the effect of phlogopite in this conductivity, which will have this, for the 37, we'll have a misfit for the fertile layer, as you might see. So this can be compensated by 10% phlogopite for the around the 100-kilometer section. Perfectly connected phlogopite is on my side, which is like a hard thing to expect actually. And then for the 40.2 milliwatts over meter square geotherm, we only need like very few percent of perfectly connected phlogopite, which is probably not the case for to be super well interconnected. So we think it is the phlogopite for this 40.2 is probably negligible, its effects. So as I say before, like the fertile layer appears to be this there's inconsistencies increases in the depleted layer, and compared to the fertile layer, it's more broadly sensed. And what we interpret this as that the fertile layer becomes a more pervasive feature in this area, and when the melts come through the here, it will laterally explore the area more as like a stop. And what we see, the cryptic effects of more widespread cryptic metasomatism probably in place. And in the depleted layer, we'll have somehow these melts penetrating the lithosphere is missing, like not exploring the space laterally. So it's not sensed by the MT method as a water like content and creates this increased misfit. So in general, yeah, this was the general summary, and I hope it's and good start for using this tool, and will be hopefully other people use it as well. And I also want to show that if you go into the project section here, I have a lot of other things to do. So again, if anyone wants to do something or already have a project, please contact me, and I'll do these things together as well if you want to or need to, and that'll be, I think, really cool. And that's kind of it, I guess.
Yeah, thank you. So are there any more questions, well, both for the tutorial part, but also for the last part? Okay, maybe while people are typing, just in terms of showing people how to use this, do you have the steps or the files that you use, for example, to create these figures and these examples? Are they part of the tool or the distribution, or can you find them somewhere? So that, again, like me as a new user, I can see, oh yeah, you have this resistivity model, you have these conclusions and these figures in the paper, so I can take that as a first trial to make the same, more or less.
Okay, I guess, yeah, I can do that. I didn't input any MT models as an example, but I could give maybe that's a good idea to as a separate file for here, that like this is an example using this paper and so on. And
yeah, and I think in
in
each of the papers, the choices that were made for the conductivity models and the partitioning models and the water solubility models are all written. So, for instance, in that GRL paper that Sinan showed the results from, all of the choices for those models are all in the paper. But that's a good idea that we could make those choices more accessible as like a list in the GitHub page as well. That's a good idea.
Yeah, and I think it's also a bit of how do you translate those things exactly into mate, and where are numbers that you entered or so on, because that's often the problem. Yeah, I can see from the list of models, okay, you used the whatever Kohlstedt model or Constable dry olivine thing. Yes, if I've heard those names, but then there might be a few other places where you have to enter a number here or a number there, and I think if you go through that step once, it really helps the new user to understand, okay, right, I've made this, now I can make my own variations of that.
Yeah.
Yeah, there certainly is, I can't remember the name of the file, but there is certainly a quick user guide.
Mm-hmm.
Yeah, it's a kind of a workflow chart, like in general. Can be seen here.
I think you have to click on download. I think GitHub. I'm not sure if it.
Oh,
no, it does.
Yeah. Yeah. Yeah, there is like a similar thing that we made in here.
Mm-hmm.
It's a little bit of the early version, so I might be able to update this actually. Yeah.
But I agree, and I do think, and that was, I guess, part of the motivation for doing this today, that I do agree the difficulty is in knowing which of those models to choose and which is valid for different settings. Yeah, I mean, I work in this space, but haven't been as deep in it as Sinan, and I still feel that when I'm trying to choose models. So I'm very conscious that someone who's not in it as deeply as I am will very much feel that. So yeah, I think that's a good suggestion for a way that we can help people do that.
Yeah.
Well, and actually, I have a project for you, Sinan, that you can add to, because I think what would be really helpful in this context is there's a bit like a project save function, where at the end of something, yes, you create some sort of file, and maybe there are a few other files linked to it that you can package it up, and I can then load it into my version of Mate and immediately get all those settings, how you combine them.
Yeah, that's a good idea. Yeah.
Because then you can, let's say this, or hopefully this will get used reasonably much in the community. Then somebody can put this into the supplemental material of the paper and say, we used Mate, here's the settings file. Okay, I load it in, I immediately see this is what they have, and I get sort of simmer plots, and then can play with that or vary this. Yes, I think that also helps to increase reproducibility, which of course is something that's very helpful.
Yeah, I think it's a great idea.
Yeah, I never thought of this. Yeah, yeah, that could be great actually. Yeah. It's it should be fairly easy to do as well. It shouldn't take so long.
Yeah, I think with a lot of these things, they're reasonably easy to do. You just have to find the time and yeah, put it in there. Okay, our audience is relatively quiet today. I don't see any questions appearing yet, but we have reached the hour-and-a-half mark. So I think we'll leave it at that. And yeah, people know how to get in touch with you, where to get the program. So I think as soon as people start to use it, then you will get emails and questions. And hopefully, yeah, this will be a useful tool for many people who are interested in a bit more petrological connection of their results.
Yeah, and we would love that as well. And if anybody finds bugs or things that don't work, then please let us know about those things too.
Yeah, so well, thanks to both of you for this presentation, and everybody else. Yeah, next week is Yasuogawa, so that will be interesting as well. And otherwise, have a good day or evening, depending on which time zone you're in.
Great. Okay. Thanks, everyone. Thank you.
Bye.